All right, so now in this video lesson, I am going to introduce how to do optimization problems right here. So optimization problem, in other words, any optimization problem is exactly a maximizing or minimizing problem, a problem that we are finding maximum or minimum value problems. But instead of just a strict mathematical problem like a strict mathematical problem, a mathematical setting like we have seen in the earlier video lecture, then here we apply our skill in terms of finding maximum and minimum value problem into various different applications out there. So optimization problem, any optimization problem is, in other words, an applied problem of finding maximum and minimum values problem out there. And so it is extremely important that any viewers who arrive at this video must be viewing this video after you have viewed my video about how we can find maximum and minimum value problems on a function strictly using the calculus right there. Okay, so here we go. So before the journey starts right here, I have to admit, within this video lecture, I can only deliver or offer about 2 examples right here in this video lesson. But because of the nature of these kind of problems, it is such an unlimited world out there with optimization problems. So I will continuously, even if for anyone for any student who are studying with me, and even if the academic term is over, you can always keep checking back at either my YouTube channel or the course main page that you are enrolled with me. Or for public viewers out there, you can always check back with my video channel, and I will continuously upload more videos on this kind of problems. Because it's such a big, big world out there that has for us to apply the optimization problems out there. And so as I said again, in this video lecture, I can only offer about 2 problems, but I will continuously upload individual different problems as separate videos like that for anyone to learn more and to see how as an arts how we can use we can apply maximum and minimum value problems into our real world applications. Okay, so my first example. All right, so now the wording of the problem is describing that a ranger who wants to fence an area of 2 million square feet in a rectangular field and then divide it in half with a fence down the middle parallel to one side. So the question now is, what is the shortest length of the fence that the ranger can use? So right here in this example 1, it has a lot of reading to do. But so now my advice is that anytime we're looking at an optimization problem like this, so of course it has a lot of wording for us, but our first thing to do here is to identify immediately. So I put the screen together with myself right here, but I normally advise my students when they when they are looking into an optimization problem like this, look directly into the actual question right there. The question itself is looking for what is the shortest length of the fence that the ranger can use. Okay, so now we have identified for ourselves somewhat so-called some objective, because we have to at least know what we are trying to either find a maximum or find a minimum value out of. So what is our objective here? Our objective here is to find the shortest length of fence that the ranger can use. So the shortest length of fence, shortest is another way, is another name for minimum, because it's just fence, it's just linear fence. When you buy it from Home Depot, you buy it from Lowe's or anything like that, any of those hardware stores or ACE hardwares, you buy those fence and they're selling you as linear rows of fence, and then we're gonna use that to fence around a certain yard or something like that we have. And so we want to find the shortest length of fence that we can use. Okay, and so now with that term right there, let me remove the highlight and highlight right here with the length of fence. So now the length of fence right here that we can use. But now, if we're looking a little further into the preceding, the description before that line right here, that it says a ranger wants to fence an area. So we want to fence in an area and in a rectangular field. So there's a rectangular field, and we want to fence that as an area, being that big of an area. Okay. So now that's enough for us to start tracking down some information. So on my board here, okay, so think about another advice, or you can see this as a recommendation. I recommend draw pictures. Draw as much pictures as you can when it gets into these kind of problems right here. Anywhere that you could, draw a picture, and the picture will tell you the story. And so, you see, the idea now is that you want to fence in a rectangular. That's what the wording was saying. We want to fence in a rectangular yard, right? A rectangular area. Okay. And so, in the way how any rectangular field looks, then there are always two lengths and two widths. Okay. And so, these are all completely unknown. So we have x here, x there, y here, y there. We have all different lengths right there that's fenced together and give us our field. Okay, and so now further, let's look back at the computer screen here and try to understand this piece of statement right here. And yes, it takes a lot of reading. So take it slow and read the wording of the description of your problem carefully. But so now what I see here is that, so the ranger wants to fence an area of 2 million square feet and in a rectangular field, and then divide it in half. Okay, divide it in half with a fence down the middle, parallel to one side. Okay, so that piece of information now is useful for us. This is how I'm seeing it. Okay, so here's how it happens. You can actually go either this way. See, it's divided in half. So divided in half can be either this way to divide, or we can divide this way. That's because we want to divide the area in half. And how do I know to do things like that? Because again, it says we want to divide it in half, divide the area in half with a fence down the middle, parallel to one side. That piece of statement right there is good for us right there, because see, divide the area in half by drawing a line. Cut it in the middle over here, right, with an edge that's parallel to either one of the sides right here. So that's why, as I said, we can go either this way or that way. But I see for myself it's easier to draw for me like this. So now note that if we are cut it in half like that with some fencing here, so this is some fencing as well. That is another length being x right there that we have to consider. Okay, and so think about this. We have to so the total area is, this total area here is 2 million square feet. But as far as the linear length of fence, when we thinking about buying from Home Depot or buying from Lowe's, and we have to buy enough so that we can go that edge, that edge, that edge, that edge, those four surrounding edges, and the one that cuts in the middle like that. So that's at least, we have to maintain at least that much. And so now I'm going to call myself length is our objective. So I'm identifying my objective here. Okay, our objective here is being the length, because that's what we need to find the minimum amount of length, so that we can still fence that much area, but having the least amount of length. Why is this kind of problem important for us? Think about anyone who loves doing home improvement kind of thing right here. Then think about, you don't want to waste too much money to buy unnecessarily long or too much amount of fencing, where you only need to fence some definite amount of area. Okay. And so, this is about planning so that we can make the best out of our work, out of our home improvement project. And so, because if we buy so much length right here, then we're gonna have to pay a lot for that. It's quite expensive out there for these fencing as well. So as far as the objective, we know that we want to minimize. We want to minimize the length here is our objective, and we want to minimize the length of fencing. Okay? But as far as length, see, if it's all these edges added up together, then it's 3x plus 2y. And so now once we set up our objective function right here, let's try to understand what we mean by minimize the length. You see, the idea is that when you build your fence, you want to maintain. Well, after reading the information, we want to have the area, the total area of 2 million square feet. Okay, 2 million square feet. So the idea now is that we have a fixed amount of area to fence around, but we can adjust, meaning maybe we can lengthen out this and shorten down that y length there, so that we can still maintain the same area being under coverage right there. But we can adjust these things so that we can still fence that much. But is there a way we can adjust? So think about the way how I'm talking about adjust. If we're adjusting the x right here to be either longer or shorter, then the y edge right here is also going to have to be either longer or shorter correspondingly. And so that's what it means now, that minimizing the length there means that we're going to have to find the best, so that x and y here, all these edges here all together add up in this way right here. 3x plus 2y can be the least total length, because just now I have pointed out we can adjust all these x and y. So y represent these two longer sides of our rectangular field, and then x is here, they are the shorter side right here, and there's also that length that's cut our area into the equal halves right there. Okay, and so that's why I'm trying to point out this is something we can do. But the main limitation for us right now, the main problem that keeps us from being able to do this now is that now this is our function, but it depends on two variables. Our function is dependent on two variables, because when we adjust the length and to hopefully achieve the minimum length, the smallest, the shortest length, then we have two variables that can be adjusted. Maybe we can shorten down the x, but maybe we have to lengthen out the y, or maybe we have to shorten down the y and then lengthen out the x a little bit, something like that. So we have to adjust two variables. We have not learned, at least up to our calculus level here, we have not learned how to handle functions of two variables like in this case yet. And so that is our major problem that keeps us from being able to get the problem done. But I tell you now for clear, this is our objective function. This is the function where we want to find the minimum value out of that. See, minimizing or minimize the length, or the same as in the wording it says we want to find the shortest length. That is just in a strict mathematical terms, it's the minimum value of this length as a function of two variables, x and y. Okay? But so now, how do we overcome that situation that our function here is a function of two variables? So now I wrote this information down a little bit too soon, but because I had to explain it, so I brought it up. But now let's dive further into that. And by the way, that piece of information was right from the wording of the problem. Okay, so it's from right here where, let me undo. Okay, this piece of information right here is what we need. We want an area, okay, of being 2 million square feet, right, in a rectangular field. And that's what it is, and that's how I know that the area of that field that I'm fencing, is 2 million square feet. So here's the thing. And the intention of the problem is the problem wants to always maintain that exactly, we want to always maintain that exactly amount of area being inside of this fence. We can adjust that. We can adjust the length here and adjust the width there, but we have to maintain 2 million square feet. Okay, and that's the idea right there. And so now, as I start using that term maintain right here, but area, in this picture over here, area is the area of any rectangular figure or picture is length times width, x times y. Okay, x times y. So in my picture it's x times y. But now I want to make, no matter how I adjust my x and y right here, I always want to maintain the area being 2 million square feet. So that means right here we come to a relationship. So that relationship now reads as following. I need to erase my board to make some more space right here, but now I come to a relationship that says the product of x and y must be always maintained at 2 million square feet. Okay? And so now, ladies and gentlemen, I brought in this example as part of this lecture because along with the example, as I work it out, I want to introduce a lot of terms right here. So this function, as I have already mentioned that name right here, this function is being set in the world of doing, in the world of the people who are doing optimization problems. This function is being regarded as the objective function, as you have already knew it. Okay, that's our objective function. Just here, up here, I wrote the term objective, but I was not clear because I was not clear in the sense that I intended to indicate that we just want to find a goal of what to do. But now once we know that our goal is to minimize the length and already derived our function here, we call that function the objective function. Okay, and now once we came up with our objective function, then this is the way how it is. A lot of time when you are doing a real world application, a real world optimization problem, a real applied optimization problem, then your objective function a lot of time comes as function more than one variables. Okay, so here I have 2 variables. There could be times where you deal with functions being 3 variables or 4 variables. Okay, and that's the major challenge with these functions right here, because they come with too many variables. But we only know how to use the calculus on functions of 1 variables. Okay, so, but that doesn't mean we're going to give up. So now I'm going to have to erase away the name, the terminology for this function. So another advice here, it's always best to find your objective function first. Be able to identify what your objective function is. That should always be the first thing in line. So being able to sketch is usually a useful thing that you can lay down before you come down to your objective function right there. Okay, so once you identify your objective function, then this piece of information right here, it's not your objective, but at least it's some useful information because it points out the relationship between your variables. Okay, so this equation right here came right out from the description of the problem as part of the given information. We refer to this as a relationship like this is being referred to as the constraint. In the world of people doing the optimization problems, they refer to this relationship right here as a constraint. A constraint is just simply a relationship that connects all the variables, pointing out how the variables of your objective functions are related with each other. So this constraint here, the way how it says, I don't care how you adjust your x and y, maybe you get y shorter to get x longer, or maybe you have to get y even longer and x a little shorter, but you have to always maintain this relationship. The product of x and y must be equal to 2 million square feet. That's why it's called constraint. You can adjust your variable, but you are being within this requirement. Okay, and that's why this relationship here is regarded as a constraint. But so now, that's just an explanation of what a constraint is. But here's the thing. This constraint now is, and any constraint is useful for us because, especially for our kind of problem right here, because now from this constraint, then I can divide both sides by x. It's simple work from the algebra that we can do. And so now my y variable, all of a sudden we realize we can solve for the y variable as 2 million divided by x. Okay? I just simply use some algebra and solve my variable y as an expression that is in terms of x. But now what's the further usefulness of doing this? I am now going to take this expression, which is now in terms of x, and substitute that right into my y variable of my objective function. So look at how good it brings me right here. Now my length, my total length, including all these 3 edges and those 2 longer edges right here, but now it's 3x plus 2, now no longer y. Y is now substituted by all that expression here. So now I'm looking at 2 millions. Okay, and divided by x. And so now we have just now brought our function down to a function completely, entirely in terms of x. Okay, it's now a function of x, or you can call your objective function now as a function L of x. It's the length of all the linear fencing, but that length can be measured simply only in terms of x, because y is also dependent on, relating with x. Okay. Now, is this the only way? Is this the only way that we can solve y for y as a function, as an expression in terms of x? No, that's not the only way. Let me do a quick little side work right here. From our constraints, x times y, anyone can also take your own choice of solving x for x in terms of y. So meaning I'm going to divide both sides here by y. Okay, from that given constraint, we have, these 2 are equal row, the 2 variables here, x and y, they're equal rows. And so in that way, we can solve for x as 2 millions. Okay, and divided by y. Okay, 2 millions divided by y. So that, now once we've solved out of this relationship for x in terms of y, then our length, starting out our objective function, starting out being 3x plus 2y, but now I'm going to take this expression right here and substitute that for x instead of y like my earlier work. And so now we create y equals 3 times, instead of x now is substituted by 2 millions over y. So I'm looking at 2 millions, okay, over y. And now plus with 2y. Now we wrote our objective function entirely as a function in terms of y. So really, I just want to point out that expressing one of your variable in terms of the other variable is the main goal, but is that y in terms of x or x in terms of y, that's pretty much your own choice. So it's just me, maybe, it's a tradition that when it comes to x and y, I tend to, it's just my personal choice right here, I tend to solve for a y as a function of x, that's it. But viewers, students of mine, you have your own choice to go with the other route. Just make sure you substitute properly. Okay, so let's stay with the route that I have already chosen. Okay, so now I have expressed my objective function L here as a function only dependent on x, now being equal to 3x plus 2 times with in parentheses 2 millions over x. And this function now is clearly or entirely in terms of x only. Okay, and so now from that point on, okay, so our function now, let's rewrite it, L of x. L here is for linear fencing length, okay, linear length of fencing, and here we're looking at 3x plus, now 2 times 2 millions is going to give me 4 millions, okay, over x. It's now a function completely in terms of x. And now with this function, now we can go ahead and apply our skills, our ability to find maximum and minimum value problems that we've learned in the earlier video lessons, in the earlier video lectures, right there, to find the maximum and the minimum value for this. Okay, and so that's why I said earlier that anyone arriving at this video, make sure you have, for anyone who now arrive at this video, make sure you have watched my other videos on how to find maximum and minimum right out of a function like this. Okay, and so function like this, you can also rewrite it as, for the next step, it's better that we write it as 3x plus 4 millions, okay, times x to the negative 1. All right, times x to the negative 1. Okay, so now, see, so now it comes to just the standard finding maximum and minimum value problems. I am going to take the derivative because we are about to find critical values. Okay, and so now first term gives me a 3, second term gives me minus 4,000, 4 millions times x to the minus 2 power, or we can rewrite this as 3 minus, there's 4 millions divided by x squared. Okay, and so now I am going to solve this. I am going to set this because we need to find critical values. So just like that, in the usual math work, then we use f of x, g of x, h of x, but here it's L of x. Why not working the same way? It is exactly the same method how we're doing. So first thing, I need to find the critical values right out of the first derivative. So I'm going to set L prime to equal 0. That means it leads to 3 minus 4 millions over x squared to equals 0. And at this point, viewers have your own independent route to solve for this equation. Basically, our goal here is to solve this equation for x. Okay, and so I choose to go with, and this equation, as a quick reminder, is the same as 4 millions okay, over x squared. I wrote through x cubed. Apologize for that, but so x squared and that, all that equals 3. Okay, so it's equivalent to something like that, and we can quickly rearrange this ratio with the other values around, and we come down to x squared here will be equal to 4 millions over 3. Okay, that's just by simply rearranging. The closest reach anyone can remember is cross multiplication. So x multiplied with 3, and then the 1 multiplied with that, and then divide both sides by 3 right here. That's how I ended up with that. Okay, it's always it's always an over 1 like that. That's how we thinking. Okay, and so now as we come to this point right here, I need more board space. So now my value for x, at this point I have expressed my equation here as x squared equals 4 million over 3. But 4 millions over 3 is already a value itself, a known value being positive value. So now I can solve for x by simply taking the square root. Now, strictly as a mathematical problem, then when we take square root, on both sides we always have to end up with positive and negative square roots, meaning we have two answers. There's a positive answer, and there's a negative answer, like in this case right here. Positive plus or minus square root of 4 millions, okay, over 3. All right, but then think about this. Now when we're actually doing an optimization problem, that means it's a real life application, and each of one of our variable here has a meaning. So x here in our case means it's a length. The length, how much length we putting on this side right here, okay? And even the y variable also has a meaning. It's also another length on the longer side of our field right here. So in that way, one thing we know for sure, x and y must be all positive values. It's an actual length, so we can't go with negative length, okay? So in that way, even though we have come to two different expressions, plus and minus square root of all that 4 millions over 3, but now according to the practical situation here, then we are ruling out. We are ruling out the negative sign. Okay, I'm taking out the negative sign. So our final answer here is only just x equals square root of 4 millions, okay, over 3. Okay, and so for now I am keeping that value in exact precision right here, so that later on when it's just my personal habit that I always keep the rounding only to the very last step like that. So right now it's not my last answer, so I am leaving that there in exact expression, 4 millions over 3 in a square root right there. So now we found that value, and we refer to this value as our critical. This is our critical value right here. Okay, it's a critical value for this function. So at this point, let me clear out some space on my other board right here, and we're gonna pick up some more steps. Okay. Right, so let me just simply remind that our starting function was, I have to write it up here in case anyone will eventually forget, but the beginning length was 3x plus 2y, and that was our objective function, and our constraint was xy to equal 2 millions. Okay, that was all we had right there. And then now, so in this way, we came to expressing our the function, our objective function, as an L of x. So this is our critical value. And so now I am going to, so at this point, it is just us to decide, is this critical value giving us a maximum or minimum? Okay, so we did all that work. We used the derivative, and we set the derivative equal to 0, and we came down to that critical value. So a critical value can be a maximum or can be a minimum. So it is now up to us to check, to test whether this critical value would be a maximum or minimum. Okay, but now you have also learned that we have two different choices. We can go with the first derivative test or the second derivative test. So I would say in a problem like this, go with second derivative test would be a little bit faster, because here, okay, so now allow me to erase this board. So our L prime prime, our L double prime here is going to be my, okay, let me quickly refer back to the other board right here. This was important for our next step right here. That was L prime. Okay, so now our L double prime here is going to be positive 8 millions. All right, times x to the negative 3 power. Positive 8 millions times x to the negative 3 power, or another way of writing that, okay, another way of writing that is going to be L double prime of x equals 8 millions, okay, over x cubed. Okay, so that's our second derivative of L of x. And so now, simply I am going to substitute my critical value. So I am going to evaluate L double prime at square root of 4 millions over 3. Okay, and that means we are going to look at 8 millions divided by a crazy expression, but it won't be that bad actually. Square root of 4 millions over 3, but all cubed. Okay, but now look at this. Really, let's be a little bit creative here. We don't really need to worry about the actual final calculation value, because using the second derivative test is all about checking for the sign of our final second derivative value at this critical value. And so in that way, I'm not going to worry about using a calculator to handle the, and see, we don't need to get the actual value, final value for that. what is the sign of this overall answer right here? So I'm pretty sure that's a positive. Inside the root here, it's all positive, and the root itself was a positive root, and we raise it to a third power. So it's all, in the end, I have to ensure that this is going to be a positive, whatever it can be. And I'm not even going to worry about getting the actual value, but being a positive second derivative at that critical value is what matters for us here. Okay, so now that is just simply enough for us now to say, okay, so I really have to erase this work. Okay, and so now all we know is this value is positive. That's all we know. And so in that way, now we can say that, okay, we got a critical value at this thing right here. It's a little bit narrow of that little space right there, but the function L double prime at that critical value is positive. So that means our function L of x here has a minimum. And of course, this is a local minimum, right? Has a local minimum at x equals square root of 4 millions. Okay, over 3. And that's, so we just now made our conclusion. So we always have to ensure that at our critical value, it will give us what we need. What we need here is that we want to find the shortest, the minimum length for here that we can get, okay? Because it saves us some cost, some money that we have to pay out of pocket right there. And so at this value for x, and remind yourself, x is how big of the, see, back in my rectangular picture right there. So x is here, and x is here, and x is here. So if we can adjust x to be whatever close to this expression, square root of 4 millions over 3 right there, and then the y will fall out accordingly. But then once we get to that x, once we adjust x right here to that expression, to that amount, to that value, then we're going to reach the that's going to be our least length after summing up all of these edges together. Okay, but now let's look back at the description of the problem a little more closely right here. Okay, so now I'm going to remove out all the highlights right here. So what is the shortest length? So now again I'm highlighting that. So I want to find the shortest length. What is the shortest length? That means we are not going to stop here. This is only indicating that, hey, at this adjustment, if we adjust x to this value, then we're going to achieve our goal. We're going to achieve our shortest length of all the linear expression, of all that linear length being expressed as following. But in the end, we need to find out how short that can get, or how low as a function graph that can be. But in a practical situation like this, how short it can get. Okay. So that means we need to, so our minimum, okay, or here let's use the practical term right here. Shortest, okay, shortest length. Is simply just the function L at this critical value we have found. So square root 4 millions over 3. Okay, and now we're going to go ahead and do the actual calculation here. So now allow me to erase a part of my board here. So in this little narrow corner of my board, allow me to start doing some calculation work. But L of x, now recall that we have expressed L of x as 3x plus 4 millions over x right here. Okay, so 3x plus 4 millions over x. And so now L of 4 square root of 4 millions over 3. Now we're looking at 3 times square root of 4 millions over 3. Okay, and now plus, and now I'm looking at 4 millions over, now there's a square root of 4 millions over 3 there. Okay. And that's how, so after doing a calculation for this, we are going to be looking at our final, the shortest length we can get right here. And so now allow me to do some quick calculation here. All right. So now my final calculation came out, and so this is the last answer where I'm going to go ahead and put that in decimals and round. So this is going to be around about approximately, okay, it's about approximately 6,928 and about 0.20 or just 0.2. Okay, that's good enough. And when it comes to rounding, then make sure, for any viewers, if you're learning from any instructor, then make sure you watch for your instructor indication of how far your instructor's requirements of how far to round. Okay, but in this video here, I am going to use 1 decimal. So the length there, when we adjust x to this value right here, then we're going to reach to, actually this is not the length. This is square feet. This is the length, but the shortest length of the total of all the fence. So that's in feet. Okay, and so after we can adjust x to this value so that all of these 3 sums here, these 3 edges, and together with the 2 y's here, it will sum up to become that, and that's the least fencing that we need right there, that we can get. Okay, and so that's how we achieve our problem. So I am going to erase the board, and let's highlight a couple important steps right there before we head out to another example. And then so once you have, hopefully after seeing my lecture here, and hopefully I have shown enough details, then you should be able to check this generality, because there is no hard rule of how you solve these problems out there, but there are a few there are certain guidelines that you can always rely to, and I hope I point out that guideline right here. And the major problem with anyone in any language, when you're working on an optimization problem, it's about when you read a worded description and try to identify your goal right there. That's the most challenging part. And so normally this is how I have been successful, so I'm sharing that to everybody. So usually when I'm doing a problem like this, then first step I'm going to have to identify, the first big step is to identify that's why I introduced that term earlier, the objective function. Okay, identify the objective function, but being able to identify your objective function right there usually requires you to write directly into, I would call that the ultimate question. Ultimate question, maybe it's a little bit weird of saying that, but it's just the very last, the very ending question that tells you immediately what to find. So back on the computer screen right here, this is what I call the ultimate question right here. What is the shortest length? See, the whole problem is a question. The whole problem is a question, but these are more like anything above that is really just information. But now the real ultimate question is here. So we read right into that one. Usually it's the last question, but sometimes it might be out of this order as well. So I call it the ultimate question because it is the real question. Anything else is just extra information. Okay? And so you read the ultimate question and identify for yourself what's your objective, and then from there we're going to be able to identify your objective function. So it's sort of like 2 little steps in there. You got to know what your objective is, and from your objective, so in here our objective was the length of all those edges that adding up. Okay, and from there we can depending on how the problem describes it, we can come up with our objective function, and that's what it is. And so now the next big step is to identify. We're gonna have to, once again, after you have identified your objective function, then we're gonna jump right back into the wording description again and identify identified the constraints, okay, and now I'm going to have to put the plural in optional parentheses right here. That means our problem we just had, that was only one constraint. X times y equals 2 millions. That was only one given constraint. Other applications out there, you might have 3, 4. I have taught courses where there are like 5 or 6 constraints right there. So those are all the constraints. So the constraints, what's good about the constraint? The constraints points out the relationship between your variables, because usually this objective function right out from the box that we have identified it might contain more than one variable. And so that's why identify the constraint is extremely useful, so that we can reduce our objective function down to a function of one variable. So think about back in the step right here, our objective function was right in the problem we just finished doing, 3x plus 2y, functions of multiple variables. We don't know how to handle something like this directly unless we have to be sitting in a much more advanced course in mathematics. And then once we identify our constraint, in our case we only had one. Okay. So our goal was to use that constraint and solve for one variable as an expression in terms of the other variable. And from there we are able to substitute that back into our original objective function and reduce that down, simplify that down, or reduce that down to only one variable. Or we're looking for our best. We're aiming at our best to eliminate the amount of variables in our objective function. Okay, and that's the whole idea. And so now once we've had after these two major steps, and successfully bring your objective function. So use your the constraints. And that's what I was saying the whole time. Use the constraints to eliminate. Okay. And bring objective function to one variable. Okay. My wording might not be that exact, but if you have been watching the video closely, you will understand what I mean by bring objective function to one variable, because it started out with more than one variables, and we brought it down to a function of one variable. And that's what I meant by that, bring objective function to one variable. Okay. And then from after that, then we can just apply the standard method. So once we can successfully bring our objective function to one variable, then all that work you have learned from my earlier video lecture about how to find maximum and minimum problem will come out. So that would be our step 4 of doing an optimization problem. So step 4 here is just simply to apply, the steps, or sometimes I might refer to that as a pretty standard step. Okay, standard steps. Okay, to find maximum or minimum values of the objective of our objective function. Okay, and that's how it is. Okay. And so now that's a general guideline I introduced here, and hopefully it brings up a good enough generality that anyone can be successful in terms of finding solution to optimization problems out there. Because as I said, there will be no instructor that can show every kind of optimization problems out there. Trust me, every day there is a new optimization problem that comes out. It all depends on what kind of work, what kind of professions you are doing. Okay, so now I am going to erase the board, and let's look into another example. And then after we're done with the next example here, then as I said again, keep checking back. Either if you are just a public viewer, then keep checking back to my video channel, and you can find I will keep uploading more videos on how to do these optimizations if I keep seeing more fascinating and more interesting problems. Okay, and the problems I will later on upload will cover hopefully as many different areas of application as possible. So now I am going to all right, so now let's look at our next example here. So now let's spend a minute or so to read the wording description of the problem. So let's say in this problem we have a cylinder is being inscribed in a right circular cone of height 3.5 and radius at the base equal to 7.5. Okay, now the problem is a little bit unclear about the units right here. You can go with centimeters, you can go with the inches or whatsoever, because when it comes down to an actual math problem, units shouldn't matter too much. So what are the dimensions of such a cylinder which has a maximum volume? Okay, so what are the dimensions of such a cylinder which has maximum volume? So now when reading that, let me highlight this now. We want a maximum volume. We want the maximum volume. Okay, that immediately gives us. So now in example 2 right there, that's our objective. See, now after example 1 and I formulated that the general guideline. Now you're gonna see in this example how I stay really close with that guideline right there. First thing is, see right there, there was a reason why I looked right into this is what I call the ultimate question. So right here in this ultimate question, I found that I have an objective. I want a maximum volume. Okay, so that's my objective. Before I can successfully nail down my objective function, then here at least I have a goal. I want a maximum volume. All right, that's what I want. I want a maximum volume. And so now a volume of what? We want a maximum volume, but volume of what? That's why now we're going to keep diving a little further. And now see, we want, of course, here according to the wording, it's the volume of the cylinder, right? Cylindrical cylinder. Okay, so such cylinder which has a maximum volume. And so now that is enough for me to track down right here. The idea is we want a cylinder. See, circular cylinder is like that. This is the base, this bottom base, top base. Okay, this is height, and the base is in circular shape right there. So we can call that here the radius of the base right there. All good? So now, so with this, now it is your responsibility to know, and like I said, when I was teaching in my video lessons on rate of change and related rates, for example, I already had an advice that you gotta, and these information is available as reference over the web, all over the web. So if you don't remember how to find volume of a cylinder like this, go ahead and hop on Google and find out. But here in this video, I can remind you right now that volume of any cylinder is going to be, you see, it's the concept of volume is just the area of the base, but the area of the base multiplied with the height. It's always the area of some floor, okay, and multiplied with how vertically height stands up it is. So area of the base times the height, that's the main concept for volume of any shape right there. So the area here is being a circle, so area of a circle is pi r square, but now multiply with the height. We got the volume of that cylinder. Okay, so this is our objective function. There you go. We want the maximum volume, the volume of the cylinder right here. Okay, we want the volume of the cylinder. So now you can recall for yourself a volume of a cylinder is pi r square times the height. Okay, now allow me to erase this sketch because I want to sketch that together with the other information. But hey, see, this is where we got past or we got done with our step 1 right there. In the guideline, we found our objective function. V equals pi r square h. That's our objective function. Right, this is the objective function. All right, and so now let's now dive back and look further into the description of the problem to get ready for the next step. Now we're going to identify the constraints, because now see, look at what's challenging about our objective function here. Our objective function involves two variables. There's the variable that's being the base, because remember in that cylinder that I already erased, okay, you got a base being a circle, okay, and your height. So you can adjust the height to be shorter or higher up, and you can make this radius of the base being smaller or larger. And so as you change any of those, the volume of your cylinder is going to get, two different volumes. And that's why, it's a function of two variables, and that's why we can find, hey, where is it to give us the maximum volume. All right. And now here's the next thing that comes up with the constraints right here. So now we're looking for the constraint, because the constraint now is going to give us a way to reduce our function down to one variable. Okay, so now we need to look back into the wording of the problem here. I'm going to clear out all the highlights here. So this piece of information now is important. A cylinder is inscribed in a right circular cone. Okay, so let's right there at that piece of information is already enough for us to make a good sketch right now. All right, so a right circular cone. It's just a formal, precise description of a cone as you usually know it. There's a bottom base right here being a circular shape, being a circle, and then it's just standing straight up, okay, like a Santa Claus hat right there, or just, see, we call it on standard, it's just a cone, any cone. But formally we call it as a right circular cone, circular and right angle right here from any base, any radius of the base out to the height right here. That's why it's called right circular cone. That's formally speaking, but normally it's just a cone. That's how people are calling it. Okay, so the idea of this problem is the cylinder that we're looking for maximum volume right there, the cylinder that we're aiming at maximizing the volume is the cylinder that's being inscribed. This is how we're inscribing it. Think about inside of that. Inside of that, we put the cylinder inside of that. So the height of the cylinder hits to the sides of our cone right there. That's the idea. Okay, the side of the cylinder hits to our cone. And so now maybe I should get on the other board and draw a better picture, a bigger picture. So here's our cone. Here's our cone. Okay, circular base, and so the height is here, right in the center of the circle at the base. And so now our cylinder can be like this. Okay, that's the sketch that I'm trying to do like that. So there's our cylinder. So this is the height. This is the h right here is the height of our cone right here, and from the center of the base, and we're looking at that's radius. Okay, that's the radius of the cylinder, and so that's why we had that formula: volume equals pi r squared times h right there. Okay, and now let's look for further information. In the description of the problem, this cone has, see, this right circular cone of height 3.5 and radius at the base equals 7.5. Okay, so now that information, this is what it tells us right here. This bigger circle is the base of our cone. Okay, so that radius is fixed. 7.5. We can call that centimeters, we can call that inches, whichsoever. This is the height of this is the height of the cone from that bottom to the tip right here. So that much height right there. That is about 3.5. So forgive me that I'm a little bit off scale. Well, that doesn't look like 3.5 in a ratio with a 7.5 here, but forgive me on that. In the end, I'm not an artist, okay? But so now, and so this small distance right here is our, this really small distance. I'm putting a little arrow here. That's our radius, the radius of the base of our cylinder. Okay, so here's the thing. We still don't see much about, we don't see much information regarding the constraints here, but here's how we can see it. Because here's the thing. We can adjust this cone here in a sense that we can see the cone is called inscribed. This cone is supposedly inscribed. This cone is inscribed. Okay, in a right circular cone, and inscribed means that's how I was drawing it earlier. This is inscribed, so meaning you can make this radius bigger, but if you make your radius bigger, then I guess that circle of that circular base of the cone is, the circular base of the cylinder is getting bigger, but we can only reach. Let me draw in blue ink right here a larger version. A bigger base version. Okay. A bigger base version is like this. Okay, so maybe it's a bigger base right there. So, but when the base gets that big, then the height has to get shortened down. Okay, that's something like that. Okay, so the height, so you can see that due to the fact that the cylinder is being constrained inside of the cone, and as we adjust the radius, then the height also needs to be adjusted accordingly. So there's a rule, there's a relationship between R and H that you can see already, and that's the constraint we're hunting for. You can now, I'm just pointing out that I sense, and you should now be able to sense that there is a relationship. There's a way to constrain. There's a constraint that tied down between H and R right there, of any cylinder on our board. Right there. All right. So now I'm really short and narrow at space now. So let me erase this picture and draw a version like this. Or let me come to the other board, because I want to come back to that picture earlier. Okay, so think about if we take a straight, looking straight at the picture of the cone, instead of seeing in 3Ds like how I was trying to draw earlier. If we're looking straight in a flat view, over here. Okay. If we're looking straight in a flat view like that. Okay, then this is a flat picture. If we're looking straight at it, if we put our eyes here and looking straight into it, in flat view, okay, that's what I'm saying, instead of 3D view like earlier, then this is the height of this is 3.5. Okay, and from here to here, that's 7.5. And then if we draw the cone is going to be in a shape like this. We draw the cylinder. This is what the cylinder looks like inside of the cone. That's why it's called inscribed. Okay. And so this much here, this little space here is radius R. So R is from the center out to anywhere there. Okay? And H is here. So think about if R is only that small, then H needs to be up here because it's inscribed. It's inscribed. Okay? So now I can actually now point out something. You see, if we are formulating this as a triangle, right triangle, isn't it? Okay. And in that triangle, if I'm looking at, there's another smaller triangle, a smaller scale, but same kind of triangle, but in smaller scale from right here. Okay. So now it's actually this problem taking us back to the concept of similar triangle. So now here's how I see it. Okay. This edge here, the longer edge, is corresponding with this smaller edge right here. So that smaller edge where I'm putting this smaller edge from here to here, that's smaller version. That is 7.5 is the total length from the center out to one side. Okay, 7.5 minus R, that's the smaller edge. So 7.5 minus R over 7.5. Setting that up as a ratio, then now you can see that this side edge right here is corresponding as two similar triangles. There's a smaller version and there's a larger version. So this edge here as a ratio with the longer edge correspondingly. That's why I'm looking at 7.5 minus r over 7.5. That ratio should be equal for the rest of the other pairs of corresponding sides. So now if we're putting h over 3.5, it should be the same ratio. So 7.5 minus r over 7.5 is the same ratio with h over 3.5. Okay, h over 3.5. And so in that way, now this is our constraint. This is our constraint. As long as we recognize somehow the two variables are related, because it's the way how the problem is describing it. Right? There has to be at least one constraint in there. I mean, I'm lying a little bit. There could be time that we're working with function that has completely no constraint at all, and it's still going to work. Like the problem that we did entirely in the video lesson, where it's only about finding maximum and minimum, where our function was already known to be just one variable. Then we could just work it out without any constraints. Okay, but here usually we need some constraints so that it will help us to eliminate the variable. So here for this problem in particular, this is our constraint. Okay. So now, if we need more constraints, we'll look for more. But let's see what this constraint can do for us. So we are now at step 2, right there, and about the end of step 2. And like I said, if we need more constraints, we look for more. But now, once we had some constraints, we're going to have to use the constraint here and solve for one variable. You can make your choice. I see that it's simpler. It's simpler to solve for h, so I'm going to solve for h as an expression of r right there. Okay, and so now allow me to get on the other board and clear out my picture here. So in the end, I didn't need that earlier picture at all. So 7.5 minus r over 7.5 on the left-hand side here equals h over 3.5. Notice on the left-hand side we can break it down into two separate terms already. Okay, and so that means in my next step I can multiply 3.5 cross multiplication. Okay, it's cross multiplication, and so in that way h equals, so I have the 7.5 minus r over 7.5, and we're multiplying that with a 3.5. And that's how it happens. And so further I can, and as I said earlier, this part right here, or it was originally the left-hand side of our equation there, we can break it down as, see, two terms in the numerator and over one common denominator. So we can algebraically break it down into two separate terms. So the inside the parentheses here becomes a 1 minus r over 7.5, and multiply with, in parentheses, multiply with 3.5. And so now it's just a simple distributive law right there to multiply the 3.5 into each term of our equation. So now I'm looking at h. So my next step here, in my next step, h equals to 3.5 minus, now 3.5 over 7.5, I'm deciding to write it as a separate coefficient, multiply with r. That's what my constraint has become after I rearrange my my constraint as a relationship, as an equation. And so now look at how useful that is, because now what's good about this point, once we have solved for h in terms of r, now I'm going to take that, okay, and substitute the h we have found into this expression for h here. So the entire expression, 3.5 minus the ratio 3.5 over 7.5 h, r, will be substituted in here. Okay, so now this is the next step. This is about step 3, where we use the constraint to eliminate our function down to one variable over here. So now v equals pi r squared. H now can be substituted by 3.5 minus, I need a little more space here, so 3.5 over 7.5 r. Okay. All right, and so now at this point we are entirely in terms of r, one variable only. Okay, and so a simple distributive law now, it's going to give me, okay, pi or multiplying the pi r squared to the first term, I'm looking at 3.5 pi r squared minus 3.5 over 7.5 pi r cubed. And that's what I meant by now we're looking at a function. It was our objective function here, the volume function. Okay, but volume as a function entirely in terms of r. Now I'm a little bit regretting that I regret a little bit that I erased that picture I drew earlier on this board here. But it's okay. We can quickly reconstruct one. But so in our cone like that, right? So like as you have seen now, r can be adjusted because r is from the center out to here. So if we adjust r, then the height will be adjusted as well, and that's the regulation for how we adjust height. But now once we adjust height, in the end, the whole volume now is only depends on r this distance. Okay, and so just simply change one distance, simply change one variable right there. The other variable changes accordingly. So the volume here in the end only depends on how we changes r. All right. So now this is a function, in other words, v of r there. And that now brings ourselves back to the standard calculus problem right there. Okay, so now I am going to, so now this is we're about getting into step 4 right there. We are going to apply the standard calculus work to find maximum and minimum problem. So that means my first step here is to take the derivative. Okay, so v prime of r, or dv dr, okay, then that is going to give me, so multiplying the 2 down and that, it gives me the 7 pi r, okay, and minus, and so now 3.5 over 7.5 times 3, okay, times 3 pi r squared. And I don't want to rush immediately into the math, even though anyone can, well, watching this video can go ahead and multiply all this together. With, I don't think it's important. Okay, and so now that's our derivative. So we're just simply going to spend some time solving this derivative for zeros to solve for r here. So setting this derivative equals 0 and solve that for r. That's precisely what it means like that. So I am going to move on to the other board right there, and let's get ourselves ready for finding critical values. Okay, so now on my other board, now I'm setting my derivative 7 pi or minus 3.5 over 7.5 3 pi times 3 pi r square is set to equal to 0. And so now let's clear out a couple of things here. The pi here can be cancelled away, okay? And so now we're looking at 7r minus 3.5 times 3 over 7.5. That is one coefficient over 7.5 right here. Okay, times r squared equals 0. And so this is in the end actually a quadratic equation. There's the r squared term with a coefficient, and there's the r term right there. And I mean, I didn't even have to multiply and divide all of this out because it's going to make the expression more messy, but it's actually a lot simpler to solve than first time we're looking at it, than how we think in the first time looking at it. Because now I have a common factor r right here. I can quickly factor out the r. And now I'm going to end up with r. I can end up with 7 minus whatever comes out from 3.5 times 3 over 7.5 r. Okay? And all that there equals 0. Okay. And so that means we can easily come up with two solutions. One of them is R. See that product, that factor in the entire product right there will become 0. That's one of it. The other one here is coming out from R equals, coming out from setting 7 minus 3.5 times 3 over 7.5 R to equals 0. Okay, and so we can quickly rearrange this equation and solve for R value right here. So that equation turns into giving me R equals 7 times 7.5 and divided by 3.5 times 3. Okay, and so now I'm ready to actually use an actual calculator to get some calculation done for this. So allow me a minute or so. All right, so my calculation came out to be R equals 5. Okay, so what have we found here? We found two solutions to this equation which came out from setting our derivative, our first derivative equals 0. So we came to two solutions. But now, again, we are not only doing a standard maximum or minimum value problem. We are doing an applied problem, a real-world application problem. And so think about the meaning of the R. R is our radius of the cylinder. R is the radius of the cylinder. So it makes no sense. It makes no sense. We won't even have a volume if we squeeze the radius all the way to 0. So it makes no sense. So in that way, we can't take, what I'm pointing out now is that we can't take this solution for our critical value. So the only choice of critical value we have left is R equals 5. That's our critical value right there for deciding whether we're going to have a maximum or a minimum volume on this objective function of ours. Okay, and so now we're getting so close, aren't we? We're getting so close, aren't we? So now, after we have done, now I'm going to spend a minute or so to erase my board here. So now the next step, but this is still in the big step number 4 here now, which is apply the standard steps to find the maximum and minimum value problem once we have found our objective. So now just keep in mind that here I'm just going to write it down here to note for ourselves right here. We got a critical value decided to be at R equals 5. Okay, so now it is our responsibility to take the next step to decide if this critical value going to be giving us a maximum or a minimum. Okay, and so in that way, again, I see that the second derivative test would be a little bit faster in this case right here, because we have already found our v prime here. So I'm just going to simply take one more step of the derivative right from there. Okay, and so now my v double prime of R. Even though you can also retry or restart any of these steps using the first derivative test, but you will have to run through the sign chart and all that. Here, the reason it looks like 2 examples so far, I've been staying with the second derivative test simply because I'm very short at board space up here. Okay, and so my v double prime here is going to be 7 pi for the first term, completely constant, minus, and now the other term multiplying down with the 2 right there. And I'm looking at 7 over 7.5 multiplied with 3 pi R. Okay, and I don't need to calculate out all of these coefficients yet. And so in that way, I'm going to quickly substitute my critical value into this double prime right here, this v double prime. So v double prime at 5. Let's see what kind of value we have. And remember, ultimately what we're doing here is we're checking for the final sign of our double prime, so we don't need to worry. So maybe if I'm off a little bit with the calculation, please forgive me on that, but the final sign is what matters for us here. And so 7 pi minus 7 over 7.5, okay, times 3 pi, okay, times 5 here. Okay, so if it's a little bit too challenging to find out, and you can see that you see there's at least there's a common factor of 7 pi here. I can factor out a 7 pi. Okay, so there's a 7 pi being positive, and here after factoring it out, I'm looking at 1 minus, right? And here is a 15 pi over 7.5. Okay, so 15. I mean, we don't have pi anymore. Sorry, we shouldn't have pi here. Okay, I apologize for that little mistake. But so 7 pi factor out, 7 pi factor out, we have left in this second term here 15, right, over 7.5. And I don't even need a calculator pulled out right here, because clearly speaking, 15 in a fraction where numerator is bigger, is exceeding the denominator, then the overall fraction has to be above 1. It's the rule for math right here. I mean, trust me, at this point that you have, when you made it this far into calculus, start making use of a lot of things you have learned. I believe you have learned enough already. What matters is how you bring it in to work, and it saves you from, see, for me right here in front of the camera, it saves me from swinging back and forth between from here and the calculator. So I'm sure that this thing here has to be negative, because like I said, this fraction itself is above 1. So 1 minus something above 1, it has to be a negative value and multiply with a positive here. So now, without the need, disregarding the actual answer, all I care is this second derivative at 5 has to be negative. Negative. Okay, we know that we're going to have a negative value. And like I said, I don't have to hop back and forth just to grab the calculator and do a calculation work like that. What's good about having a negative second derivative at the critical value here? Because now that's enough for us to make our final conclusion. Okay, so all right, so in our, what it says now is that V of R, right, has a maximum at that critical value or equals 5. We made a conclusion. Okay? So V of R, the volume here, has a maximum at or equals 5. Okay, so before I rush into finding the actual maximum volume, let's read the problem one more time carefully. Because what it says here, what we have come here is the value, or in a practical meaning, this is the dimension of this is one of the dimensions of your cylinder that determines the volume of your objective. Okay? And so let's read our description one more time right here. I'm going to remove this highlight, which is no longer needed. What are the dimensions of such cylinder which has a maximum volume? If we're reading the questions a little more carefully, the question is not looking for how big the volume is. Let's just say when it hits, the other meaning of this question is when it hits a maximum volume for that cylinder, what are the dimensions there that decide the maximum volume, that brings our cylinder to the maximum volume? That's the art of the problem right there. So now in this actual optimization problem, we're almost done. We have found one dimension already. So R equals 5, that's one of it. Okay, R equals 5, that's one of it. Okay, now if you took note throughout the entire example I've done so far, then you can roll back to an earlier page. I had to erase my board up here, so I have to rewrite it a little bit. But this is one amount of dimensions. Because recall yourself again, in the picture, the radius of the base is one dimension, and the other one is another dimension. So we have found that H is equal to, okay, Okay, so if I recall correctly, then it's 3.5 minus 3.5 over 7.5 R. Okay. All right, so that's my H right here. That's how I expressed H as an expression in terms of R. And so now what's good about having found R equals 5 here? Now we can just substitute R into our expression for H here to find the value for H, and there we find the other dimension. So now H equals 3.5, and maybe I should factor it out again. Okay, factor out the 3.5. So now 1 minus, and here actually it's 5 because R now is 5. R now is 5 substituted in, so 5 over 7.5. Okay, and so now allow me a minute or so to finalize my calculation here. All right, so my final calculation comes out to be 1.67 if I round it down to 2 decimal places. But once again, if you're doing a problem like this with an instructor, with different instructors there, make sure you watch for your instructor's requirements about how far to round. Okay, but so, and what for the units here, since right from the beginning the problem never had any units, so we can make that up, centimeters. And centimeters. I was raised in using metric when I started out learning math. Yeah, so it's more like a tendency for me to use metric. Okay, but that's how we've done another problem. So this problem in example 2 is a little bit unlike example 1 in the sense that we don't need to go all the way to find out how big that volume has to be, but we only stop after we have found the dimensions that have determined our objective there, our objective maximum volume. Okay, and of course all that standard work we have learned in the lecture about how to find maximum and minimum values are being brought all in here, and this is why I said, you know, it's usually it's a direct application of right after we've learned about how to find maximum and minimum value problems.